Hello, welcome back. Today we will look at the lab work for persistent homology. Okay, this persistent homologies lab would involve three parts. The first part would be on a Ripser. Right, it's a package where we can run Vitoris Rips filtration and we can obtain persistence diagram. Whereas the second part, we will look at another package called GUTI, which represents geometry in higher dimensions. And then finally, we will look at the application of persistence diagram, persistent homology for classification work. Yeah, so we will be using GUTI again for classification, right? So let's begin from the start where I would introduce you to Ripser. Okay, so Ripser is a package which is available in Scikit TDA, right? And of course, Ripser basically has a number of packages. The package you saw previously on Kepler Mapper also lives in this package, right? So in order to run persistent homology, now you have to install three packages. The first package is Cython, second package is Ripser, and finally the third package is called persistent. Okay, so Ripser's algorithm, or rather code, is written in C language. So you need Cython in order to run Python with Ripser. Okay, so once Ripser runs, you get simplicial complex, specifically Vitoris Rips simplicial complex, and finally you would be able to visualize persistence diagram using persims package. Okay, now install once you run and uncomment this and run you get to install these packages. Once you install the package, so please run this cell and you get to see the version that you have installed. Okay, right. So the next package would be on GUTI, and just install pip install GUTI and you'll get your package as well. So the latest version for GUTI is 3.9. Okay, so if you've installed all that, now let's try a simple toy dataset. Okay, so the toy dataset that is from sklearn, right? So once you run this, and the toy dataset that we are going to use is this dataset, okay? Datasets dot make circle. Yeah, so we want 500 points with a little bit of noise, and we have two circles. So this factor would change the way this ratio of these two circles. So the rest of the codes are basically to just visualize and plot the circle. Okay, so this is the circle, two circles that you get to see. You can see it's color coded from left to right, which is in the form of X values. Okay, now we're going to extract the shapes information using persistent homology via the package called Ripser. Okay, so in order to see, so of course, in order to use Ripser, so first import Ripser, we're going to use Rips, okay, in order to create simplicial complex, Vitoris Rips simplicial complex. Okay, so once you run that, define the setting for Rips complex. So this is the maximum dimension you want. For example, max dim equals to 1 simply means that you're going to extract H0 and H1. H0, yeah, and H1 from the data set. If you put 2, you're going to extract H0, H1, and H2, right? And the coefficient is based on the dimension, the nearest, as I wrote here, the nearest prime number of the dimension of the data set that you're going to use. Only then you would be able to correctly extract your H0 or HT class. All right. And then after that, what you're going to do is that we are going to visualize. First, of course, first you got to bring in the data, and just like SQL just dot fit transform, you'll be able to get the pairs, yeah, birth and death pairs. So once you run once you get a birth and death pairs, you'll be able to visualize them. And then of course, once you put legend true and show true, you'll be able to see the labels of a H0 and H1 classes. Okay, so this is what you get. So let's relate to the data. So in the data, you can see small circle. There's one small circle, and also there's a big circle representing your data. So represents connected components, right? And H1, as you can see, represents your one-dimensional whole. So you can clearly see there's a two one-dimensional whole available in your data. Okay, what persistent homology has extracted. Okay, now, as I said earlier in the lecture, you will not be able to use this diagram directly. Rather, you have to vectorize them in order to represent it in the form of a feature vectors. To be specific, topological or geometrical feature vector, which you would be able to use for machine learning. Okay, so the first part here, we are going to vectorize your persistence into a persistence landscape. Right, so as I told you earlier, so we need this package called persim in order to convert your persistence diagram into a persistence landscape. Yeah, so we denote PLA represent landscape, and from this persims package we import persistence landscape approximation. So that is what it the function means, persistence landscape approximation, and the diagram, yeah, the diagram that we have extracted earlier, and homology, the homology degree 1, which means we just want to use H1's information to represent persistent landscape. So if I were to go up again, as you can see, there are actually two information connected components representing blue points and representing H1. So in order to use the information and the H1 information as feature vector for machine learning, we are just extracting H1. But just to be precise, both H0 has a lot of information, a lot of shape information for you to use for machine learning. Okay, so now once you are done, you have saved your persistence landscape, you will be able to visualize the persistence landscape. So this is how your persistent landscape looks like. So from persistent landscape, use plot persistent landscape or plot landscape. So there are two versions how you want to visualize your persistence landscape. So the first part here, the simple persistent landscape simple, is whatever that you have extracted from a diagram. So just run it and you get to see the layers. Right? So when you run, you get to see all the layers. There can be many layers, right? So the blue one being the first lambda, maximum lambda, second highest maximum lambda, and then green is the third highest maximum lambda, and so on, so forth. And again, remember, we just extracted each one classes Betty 1 information. There's another one, yeah, per plot landscape, that function that you can use to the landscape is called plot underscore landscape. From here, you can see that rather than representing in the term of colors, it shows in the form of y value, x value, and z value, where you get to see layer being further behind, and then the last layer being topmost in front. Okay, so it's by layer again. And just that how you can differently visualize your persistence landscape. And of course, if you put dot values shape, so your layer show, you get to see our shapes. We have like 9 layers. We can use 9 layers. So we can in fact represent this point cloud with 9 features representing 9 layers. Each layer has 500 points. Okay, feature 1, 500 points, feature 2, 500 points, until 9 features, 500 points, which represents H1 class of your data. Okay, so this is how the vector looks like. So for example, the first feature, yeah, which is PLA dot value 0. Okay, so just looking at the type, it's in fact a NumPy type. Yes, you would be able to visually or manually extract it and form of let's say in the form of pandas data frame and plot just to check really what exactly it is. How did it plot, right? For example, I'm using pandas and I'm going to transpose the persistent language. I'm going to use the first 5 layer, right? And I represent it as feature vector. So this is how the feature vector looks like. And we have like 1, 2, 0, 1, 2, 3, 4, the 5 layers of maximum layers of lambda, and the points are from 0 to 500, 0 to 499, representing 500 points, right? So you just you can straight away use pandas data frames function called plot.line. You'll be able to see exactly what you saw in the previous persims package. Okay, so that would be the end of the first part of using Ripser.